This presentation is Module 3A of Chem for Bio at Northern Virginia Community College, Annandale campus. In this module, which is split into two parts, we will explore compounds and molecules. In the first part, we will focus our attention on covalent bonding, how covalent bonding leads to the formation of molecules, and then other factors that influence the shapes of molecules and their functionality. Question for you. If I handed you a container full of yellow gas, would you open it and would you inhale it? If I put all these scary stickers all over the bottle, would you open it? Would you inhale it? Hopefully your answer is no, because the gas inside that bottle is chlorine gas. Chlorine is a naturally occurring element. It is highly dangerous, corrosive, was even used as a chemical weapon during World War I. But now look at this lovely white crystalline solid. Would you ingest this? Well, you should recognize that solid as table salt, also known as sodium chloride. Well, sodium chloride is totally safe to consume and in fact is a necessary part of every human's diet. What's the difference? Well, chlorine is an element. It comes with a very specific set of chemical and physical properties, some of which are very unpleasant. But when chlorine interacts with the element sodium, that is, when they react to become sodium chloride, a compound is produced, and the nature and the properties of that compound are usually not at all similar to the properties of the elements used to create the compound. Very specifically, an element is a pure substance that contains a single type of atom. Elements cannot be broken down into simpler pure substances, whereas a compound is still a pure substance, but it contains two or more different elements in fixed, well-defined ratios. They're whole number ratios, and it can be broken down into simpler pure substances by chemical means. Usually it can be decomposed back into its elements. So how do you make compounds from elements? Quick review. In Module 2B, we talked about how electrons were arranged around the nuclei of individual atoms of different elements. We talked about the valence electron shells and how elements prefer to have their valence electron shell completely full. That's usually with 8 electrons, but if the element is in period 1, it can only fit 2 valence electrons. And we introduced the noble gases, which were the elements in the group 8A, that rightmost column of the periodic table. They are the elements that naturally have complete or full valence shells, and it makes them chemically very unreactive. Most other elements on the periodic table want to react so that they can also have a complete valence shell. Again, for most elements that's going to be 8 valence electrons, but a period 1 element can only have 2 valence electrons maximum. One of the most important ways for this to happen is for atoms with incomplete valence shells to share electrons with other atoms in order to complete their valence shell. When this happens, an attractive force exists between the two atoms that are sharing the electrons, and that attractive force, strong attractive force, is called a covalent bond. The example given on this slide is two atoms of hydrogen, each with one valence electron, combining with one atom of oxygen who has 6 valence electrons. Each hydrogen atom shares its valence electron with one valence electron of oxygen to make 2 covalent bonds, resulting in a water molecule. This slide simply reinforces what I've just said. A covalent bond is the bond formed when two atoms share valence electrons. A molecule is, by definition, the simplest unit of a compound that still has, again, the physical and chemical properties of that compound. So we took two atoms of hydrogen and their valence electrons, reacted it with one atom of oxygen, and the result is one molecule of water, and all three atoms having a full valence shell of electrons. The sharing of a pair of valence electrons between two atoms, again, I said a couple slides before, creates a strong, attractive force between those two atoms. When it is only one pair of valence electrons being shared, we say this is a single covalent bond, one shared pair of electrons. So in a water molecule, there are two single bonds between each hydrogen and the oxygen. Elements do not have to share just one pair of valence electrons. If, in trying to fill the valence shell, two or more pair need to be shared, nature allows it to happen. If two atoms are sharing two pair of valence electrons, it's called a double bond, and it is stronger and shorter than a single bond. We represent it by two parallel lines connecting the two atoms. So for example, in oxygen gas, the two oxygen atoms, each with 6 valence electrons, well, they both want 8 valence electrons, so they share two pair. Continuing with this theme, sometimes covalent bonds are composed of 3 shared pairs of electrons. In nitrogen gas, the two nitrogen atoms, each of them with 5 valence electrons, need to share 3 pair of electrons in order for them to complete their valence shell. This is called a triple bond, and it is represented by 3 parallel lines connecting the two atoms. Quadruple bonds are very, very uncommon, particularly in the biological sciences, so we don't consider them here. So what we have been looking at, what has been drawn on these slides, are what is called the structural formula for a molecule. It actually gives you a great deal of detail. It tells you the bonding arrangement of the atoms in the molecule, who is sharing with whom. We differentiate this from the molecular formula, which simply gives you the identity of the atoms in the molecule and the number of each atom in the molecule. In biology, the structural formula is much more valuable than the molecular formula, although obviously the number and type of atoms is the same in each. So what else is important when talking about covalent bonding and creating molecules using covalent bonds? Well, utterly critical is the shape that the molecule takes. The shape of the molecule is influenced by several things. It's influenced by the number of covalent bonds, the order of those covalent bonds, whether they're singles, doubles, or triples, but it's also highly influenced by the three-dimensional arrangement of the electron orbitals. Remember, those orbitals, those three-dimensional regions of space that the pairs of electrons actually occupy. And if you remember from Module 2, these orbitals have a variety of shapes. They can be as simple as a sphere. They can look like dumbbells. They can look like dumbbells with donuts around their middles. They can look like clover leaves. They have a variety of shapes. But each orbital can only hold a maximum of 2 electrons. If an atom already comes with an orbital that already has 2 electrons in it, it will not bond with another atom through that orbital. It can't share, it already has 2. These pairs of electrons in an orbital that have already filled an orbital are referred to as non-bonding or lone pairs of electrons. Now, in period 1, there's not a lot of variation in the shapes of the orbitals. The orbital is simply a sphere. But in the second shell, in the third shell, so the second period, the third period, the orbitals can in fact hybridize into different forms to additionally stabilize the shape of the molecule that is being created. The chart on the right of this slide shows you the 6 shape variations that are most important in the biological sciences. If there are 2 atoms bonded to a central atom with no non-bonding pairs, you obtain a linear geometry or a linear shape. 3 atoms around a central atom bonded to a central atom, trigonal planar. 4 atoms directly bonded to a central atom, you create a tetrahedron. If a central atom is surrounded by 2 bonding, or is bonded to 2 other atoms, and yet also has a non-bonding pair, the shape that results is a bent or an angular shape. If the central atom is bonded to 3 other atoms and has a non-bonding pair in one of its orbitals, a trigonal pyramid or a trigonal pyramidal shape is attained. And for the last one, if that central atom is bonded to 2 other atoms and also has 2 of its orbitals with a pair of non-bonding electrons in it, you again attain a bent type geometry where the angle is slightly more acute than in the other example. So here's just a few quick examples. Hydrogen gas is very simple. Each hydrogen is in period 1. It comes with 1 valence electron. All they do is share each electron, a single bond. The molecule is linear in shape. But somebody like carbon, he comes with 4 valence electrons in that second valence shell. He comes with 4, he wants 8. So what he would like to do is share 4 times. He needs 4 more electrons by sharing. And in a molecule such as methane, CH4, that is exactly what he does. He shares 4 times, 4 single bonds, and the shape that is most stable is tetrahedral. Now, in contrast, a molecule like water, well, again, each hydrogen comes with 1 valence electron. They just want to make 1 single bond. But the oxygen comes with 6 valence electrons. 2 of his orbitals already have a pair of electrons in them, and he just wants to make 2 more single bonds. That is exactly what he does. Single bond to each hydrogen and 2 non-bonding pairs. That results in a bent or angular shape. Contrast that with carbon dioxide. Again, 1 central atom, only 2 atoms on the outside. But in this case, carbon needs to make 4 bonds. He came with 4 valence electrons. He wants to share 4 times. Each oxygen came with 6 valence electrons. They want to share twice. And the easiest thing for these atoms to do is have the carbon form 2 double bonds, 1 to each oxygen. Every atom has a full valence shell, but notice that none of the orbitals on carbon contain non-bonding electrons, so that the shape that the carbon dioxide takes is linear. Remember that water's was bent because those non-bonding pairs distorted the geometry. So that takes care of covalent bonds, and it takes care of the most elementary shapes. But here's an issue. Not all atoms in covalent bonds actually share the electrons equally. Some atoms are more electron greedy than others. This tendency, this property, is the property of electronegativity. It is the tendency of an atom to attract shared electrons to itself. Elements vary in electronegativity. The numbers have been derived from experimental data. Those numbers, the electronegativity values, vary from 0 to 4.0, and we find that the most electronegative or the most electron-greedy elements in a covalent bond are fluorine, oxygen, nitrogen, and chlorine. And these electronegativities do influence the nature of the covalent bond. Nonpolar covalent bonds form when the 2 atoms who are sharing the electrons have similar electronegativities. They need to be within 0.5 electronegativity units of each other. In that case, the electrons are shared equally, and the distribution of the electrons in that bond is very symmetrical. But polar bonds form when the atoms differ in electronegativity. If the difference in electronegativity is greater than 0.5 units, then the more electronegative atom actually pulls at the electrons more, and it results in an unequal distribution of the electron charge in that bond, and it actually results in a partially negative charge that is localized around the more electronegative atom in that bond. This will affect the overall polarity of the molecule. For example, methane, CH4, contains 4 carbon-hydrogen single bonds. Each of those bonds is nonpolar because the electronegativities between the carbon and the hydrogen are very similar. The distribution of the electrons about this molecule is relatively equal, relatively even, and consequently there is not a localized negative or positively electrical end to the molecule. But you contrast that with water, where the oxygen is more electronegative than the hydrogen, and the shape is bent. So the oxygen-hydrogen bond, each of them is polar covalent with a distribution of the electrons closer to the oxygen. You combine that with the bent shape, and you find that the water molecule itself has a slight negative electrical charge localized near the oxygen atom and a slight positive electrical charge localized near the hydrogens. This results in a polar molecule. Sometimes you can have polar bonds in the molecule, and yet the two polar bonds cancel each other out because of the symmetrical shape of the molecule. And that is the case in carbon dioxide. Because the carbon dioxide is linear, even though both oxygen-carbon bonds are polar and favor the oxygen, well, the two polar bonds cancel each other out, and the molecule itself is non-polar. So why should you care in studying biology? Why does the shape of the molecule and the polarity of the molecule matter? It's because shape and polarity strongly influence biological function. The example given on the slide, on the left is a naturally occurring endorphin molecule, and on the right is morphine. And the fact that the shape and the polarity of the morphine molecule mimics the shape and the polarity of the endorphin allows both molecules to bind to the same opioid receptor in the human body. Consequently, because their shape and their polarity is similar, their biological effect, their biological function is similar.